How does compression work, also known as zipping? What if you take several files and you compress them, and then you take that compressed file and you try to compress it? Does that file get smaller or stay about the same size? Why does compression work better with text files than it does with binary files like images and videos? And finally, what in the world does this mean? These are all questions I'm going to answer with the help of something called Huffman Encoding. Huffman Encoding is a special type of tree. Now, we've talked about trees before, and this is a type of binary tree. What a binary tree means is that we have a node, and it can have at most 2 children. The child on the left is assigned the number 0. The child on the right is assigned the number 1, which works really well with computers since we use the binary system. So we can use this to write a compression algorithm for a text. Now keep in mind how text works with computers. We typically use the Unicode format now, which is a 2-byte format for each letter. What Huffman encoding does is it uses essentially a variable byte encoding mechanism. And the most common letters have the shortest path to reach. For example, take a look at the Huffman tree I've put behind us. And let's think of a common letter like the letter E. So we start at the central, and then we go left, which is 0, and then we hit another child here. Each of these intersections of masking tape that you see represents a node with children. So we have another 0, and then to the right we have a 1. So the letter E is represented by 0, 0, 1. Now let's look at a less common letter like Z. For Z, we start down the right, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, and we get to Z. So the more common letters have the shortest path, the least common letters have a bit of a longer path. But what's interesting is that combination of 0s and 1s is unique for every single letter. So let's walk down this tree and let's use these numbers I have here. So I'll read them off: 0, 1, 0, 1, 1. So 0, 1, 0, 1, 1, 1 gives us the letter Y. Now, once we've walked this path of 0s and 1s and we reach a letter, we start all over again. So I have 6 bits I've used: 0, 1, 0, 1, 1, 1. And now I start with this next one all the way back at the top again. So I have 1, 0, 0, 0, and that gives me the letter O. Now let's start with the next letter. So I have 1, 1, 0, 1, 0, 0, 1, 0, 0. Let's see how far we get until we find a letter. So 1, 1, 0, 1, 0, 0. That leads us to the letter G. Now we've stopped at this point. And so we have 1, 0, 0, 1, 1, 1, 0. Let's see what that gives us. 1, 0, 0, 0 takes us to the letter O. And now that leaves us with 1, 1, 1, 0. Let's see where that takes us. 1, 1, 1, 0 takes us to the letter T. Now our final line, 0, a whole bunch of 1s and a 0. So 0, 1, 1, 1 takes us to the letter I. Zero and 3 1s, and that leaves us with 3 1s and a 0. Hey, that's a palindrome. I just realized that last line is a palindrome. So now we have 1, 1, 1, 0, which leaves us with T. And the final answer is, you got it. Now that's what? That's 8 letters. What's interesting is if you look at this, there are 38 0s and 1s. which means there are 38 bits. So 8 bits to a byte. Well then, 5 times 8 is 40, so this is slightly less than 5 bytes. Now remember what I said about Unicode. Unicode allocates 2 bytes per letter. So that's enough space to store about 2.5 letters. And in that space, we've stored 8 letters. So that hopefully answers the questions that I asked at the beginning of this video, which is, why is text compression so much more efficient than other types of compression? And why can't you compress a compressed file? Because what it's doing is it's effectively making use of a variable amount of space to store letters. And even more importantly, it's putting the most common letters at the top, which is what I call the Wordle strategy. If you play any of those word games and you use the common letters first, you're probably using words that have these letters, or Wheel of Fortune, La Roulette de la Suerte, whatever your favorite game is that involves picking letters. You'll find the R, S, T, L, and E letters are right up at the top. R, and I see T, L is here, S right down there. It's the most common letters right up at the top. So I hope this discussion of Huffman encoding and compression was helpful, and as always, I look forward to reading your comments. Thank you.